I did the eigenvalue problem for a 2 by 2 matrix, and we did it on paper, and we did it with Python. But it's better to see a real life example of that. So let me start off showing you this code. So I have here 4 masses that are connected by springs, and they can rotate. So I'm going to play it, and I'm going to start with this code. So there's my 4 masses. The yellow one is just a center mass because I want to rotate about the center mass, and they're not equal masses, and they're not rotating with a constant angular velocity. You can tell that because the masses don't make circular orbits. See how they're spiraling around? So the whole thing's tumbling. And this is what can happen, right? When you have a real rigid object, and this is not technically rigid, but it's close enough, the angular rotation doesn't have to be in a constant direction. The angular momentum, if you throw it up or do whatever, the angular momentum is constant, but not the angular velocity. However, there are 3 axes, at least 3 directions of the angular velocity for which this will rotate, and we want to find those. So I'm going to talk about this program really briefly. I'm not going to go into a lot of detail. We're going to use it and find the angles that we can, the angular velocities that will rotate correctly. So let's talk about the eigenvalue problem really quickly, and then we'll come back over here. Okay, so the eigenvalue problem, let's start off with the definition of angular momentum. This is what you see in the introductory physics textbooks. You'll see angular momentum L is the moment of inertia I times the angular velocity omega. For a discrete set of masses, here I have 4, we can calculate the moment of inertia as the sum of mass times its distance from the axis of rotation squared. And that's the axis of rotation, right? So this assumes that it's rotating about a fixed axis. However, if it's not a fixed axis, if it's freely rotating in 3D, then we define the angular momentum vector L as I times omega, and I is the moment of inertia tensor. And we define I as the components Ixx, Ixy, I know I have to write it all out, xz. Just calm down. Iyx, Iyy, Iyz, that's a y. Izx, Izy, and Izz. And so it looks like a matrix. In this case, we can treat it as such. And we can find these components with the following. Ixx is going to be equal to, for discrete masses, the sum over I, mi, yi squared plus zi squared. So I'm going to go through all my masses for this component right there, and I'm going to take their y component squared plus their z component squared multiplied by its mass. And then if I want to do that for y, it'd be x squared, zz is x squared, y squared. Now the off-diagonal elements, I, x, y, is negative sum over I, mi, xi, yi. And so you can do that for any of the components. We can calculate this matrix, but now we have a problem, right? When I operate I with some angular velocity omega, I don't necessarily get a angular momentum vector in the same direction. That's the problem. So what do? Well, if I want to find this. I want to find I omega such that it's equal to some constant, scalar constant times omega. And that would be the angular momentum, but the angular momentum is a scalar multiple of it. And boom, that's the eigenvalue problem. So just a reminder of how to solve this. Right? We're taking a matrix, essentially, operating on a vector and getting a scalar times a vector. One way to solve this is to multiply this side by the identity matrix. So I have I omega is 1 lambda omega. And just a reminder, the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Because you can multiply that, operate that on this vector, and it doesn't do anything. It gives the same thing back. And so that's fine. You can do this. Now I can subtract this from both sides, and I get I omega minus 1 lambda omega equals 0. And that's a vector, right? It's still equal to a vector. This is a 3 by 1 vector. Now I can actually factor out the omega, and I get I minus 1 lambda omega equals 0. This can only have a non-trivial solution. Of course, if omega is 0, this works, but that's trivial. We get a non-trivial solution if the determinant of this is 0. So that, putting it all in, I'm looking for this, the determinant of Ixx minus lambda, because once I take 1 times lambda, all these are lambdas, and I'm subtracting them. And then I have Ixy, Ixz, Iyx, Iyy minus lambda, Iyz. My y's look like x's, and I'm sorry about that. That's a yy. And then down here I have Izx, Izy, and then Izz minus lambda, and set that equal to 0. Now that is simple in theory, but not easy to do, because I have to take the determinist matrix. I'm going to get a third order polynomial with lambdas in there, and I'm going to have to solve for the lambdas, and I'll get 3 of them. And we did that with the 2x2. But we also did that with Python, and that's what we're going to do. So there's a Python module I'm going to show you to do this. So we can do this. Once we do that, we'll also find the eigenvectors omega, omega 1, omega 2, omega 3. That's what we want to find. And if I start with one of these angular velocities, the angular momentum will be in the same direction, and it'll rotate nicely. Okay, let me tell you about my 4-mass rotator, just so you can see how that works. What I have here is, I'm going to draw just 3 masses, because you could do it with 3. And these don't have to be the same. What I did was connect them by springs. And when I do that, I can calculate the force on each mass as just due to the spring force, right? If I take this and I stretch it, then this mass is going to get pulled that way. This mass is going to get pulled that way. So let's call this 1, 2, 3. This is going to have force 2 on 1 and force 3 on 1. If I calculate those forces and I calculate the net force in this mass, then I can use that to update the momentum of that mass. I don't need the moment of inertia. I'm just using point mass particles, right? It's just that I have 3 or 4 point mass particles. I have to calculate all those spring forces and then just let it do whatever it wants to do. And that's what you saw in that program. Okay, that's what we saw. So what we need to do is to take our masses, and then we need to find the moment of inertia, tensor. That's not it. Find the moment of inertia tensor using these to find all those components. And then I'm going to take that moment of inertia tensor and use NumPy Python to find the eigenvectors, and then go back and plug it in and see if I get what I get. Okay, so that's what we're going to do. We need to make a function that returns the moment of inertia tensor. And so in this case, one of the other important things is these x and y values don't have to be the x and y values of the system. I want to do the x and y values about the center of mass so that it rotates about the center of mass. So that's just a little bit easier. You don't have to worry about this external stuff. I want to rotate about the center mass so that there's no torque. Okay, so I already have the center mass, but I want to make a function that I give it the center mass, and I give it my masses, and then I'm going to return the moment of inertia tensor as 3 vectors, and then we can take that and plug it into NumPy. Okay, let's get some coding done here. Okay, so here is my my program. What I want to do is to define a function that I give it a list of masses and a center of mass. Okay, so that's what I'm going to do. Here is my, let's just go up here and do that. Let's make it up here at the top. I'm going to call this, obviously I'm going to call it I, right? So def I, I'm going to give it a list of masses, ms, and a center of mass, I'll call that ro. And I'll put a note here, takes ms as a list of masses, ro as the center mass. Now what I want to do is to go through that list and I'm going to sum up, mi, xi, ri, and I'm going to add them all up. It's a sum. That means I have to go through the list. Whenever I have a sum in Python, I need to start with a 0 value. Okay, so I'm going to go ahead and calculate some 0 values, and then we can go through and add up stuff to find the list. Okay, so that's the first thing I'm going to do. I'm going to say ixx is 0, ixy is 0, ixz is 0, iyz is 0, iyy is 0, izz is 0. And you'll notice I need 9 elements and I only have 6. And that's because right here I have ixy. Well, ixy and iyx are the same thing because the order of operations is switches. I don't need to calculate that, right? I can just use ixy. And the same thing for ixz, iyz. So I only need to calculate some of the elements. It's not a completely independent matrix. Now I want to go through my list of items in my masses and just add up, the mi times xi squared plus yi squared and all that stuff. So let's just calculate it using that equation. So the first thing I'm going to do is go through the list. For ms, right? So ms is a list. So I can go through the list item and just call each element Very useful. I'm going to calculate my ixx's. Ixx is equal to ixx plus m, right? I'm going to calculate each individual thing and add it to the total. So my total started at 0. But I need to add each one in there. So now I'm just going to add in the difference between the actual x value and the x value of the center of mass. The y. And then the same thing for z. So times, I have to do the y. So it's going to be mm.pos.y minus ro.y. Ro is the center of mass, right? And so this is a list of spheres. So each sphere has a position function, a position attribute, and that's what I'm actually getting for the location. So mm.pos.y is the y value. So that's the difference, and then I need to square that. And then I need to do the same thing for z. No, it's plus, right? Yeah, plus, squared, plus, down here, plus mm.pos.z minus ro.z squared. That's ixx. Now I need to do ixy. It's pretty easy. Ixy is equal to ixy minus, remember there's that minus sign, mm.m times mm.pos.x minus ro.x. Again, I need to find the x value with respect to the center mass, and then multiply that by mm.pos.y minus ro.y. Now I need to do, I'm looking at my list up here. Which one's next? I have ixz, and it's going to be the same thing, so I'm going to copy this. This way I don't have to type, right? No one wants to type. And now I'm just going to change this to ixz, z, and you gotta emphasize that z when you say it. And then over here, this is z. I didn't emphasize z there. Okay. The next one I have is iyz, so let's just paste that, and let's just change this to yz, and I'm just going to change this x to z because the order of operations doesn't really matter. And then I have the y. Next, I'm going to do, let's see, I got ixx, ixy, ixz, iyz. I need to do iyy. So that's going to be, let's not do that. Let's copy this one and paste it down here and change this to yy, and this is going to be x and z. Oops. And then I need to do zz. Change that to zz, zz, and this will be x and y. So I'm going to leave that as y and change this one to x. Okay, so that's it, right? I have them all. Now, just to make things easier, I'm going to make an ix vector, an iy vector, and an iz vector, just to return them all as a list. So after I do that, I can just say ix is the vector ixx, ixy, ixz, The y vector is vector, and you don't have to, you could just print them out if you want to. I x y, I y y, I y z, and then the I z vector is vector I zx, but I don't have that one, so I can say xz. Oh, did I do this up here wrong? Let's see, xy, yeah, that's xy. See, it should be yx, but I did xy. I did it right. How did I do that right? I'd usually make the mistake. I yz, which is up there, and then I zz. And thus return this as a list. Return, and this is Web VPython, so we have lists. So return the list I, x, I, y, I, z. So now I can print that. So down here, once I make my whole thing, and before I rotate it, let's just print it down here. Oh, it's in, this is, let's do it right, do it right here. So print I equals I, and my list of balls is called actually balls. Yeah. And my center of mass, which I do calculate, I did calculate this, is RCOM. Right there, RCOM. Okay. So this is going to be, what did I say? I said balls, RCOM. I think that's right. Let's just see if it runs. Okay, so it's rotating that thing like it said. And there's my moment of inertia tensor. Numerically, right? I have all the numerical values for it, and that's what I want. Now what I want to do is to use that matrix. It's a matrix. I want to use that matrix to find the eigenvectors, and then take those eigenvectors and start them off with initial velocities and see if it rotates nicely. So let's just copy this. This is a dumb way to do it, right? I mean, there's better ways to do it because I'm using NumPy, which does not run in Web VPython, and then I'm using Web VPython, which does run in Jupyter, but it's just kind of clunky, to tell you the truth. It gives me a little bit of errors. So I'm switching over here to Jupyter Notebooks. You can run this on Google Colab if you want. The first thing I need to do is to import NumPy. Import NumPy as np. I'm going to run that. And now I'm going to define my I vector. I equals np.array. And it's an array of all that stuff. Okay. Now I have to format a little bit because it's, I did something dumb. But I want to do this. I'll get rid of that right there. That's my first line. And that needs to be a square bracket. Okay, and this one needs to be a square bracket, and it adds that one other in there. I don't want that. And then I'm going to go over here and change that to a square, and then change this one to a square, and get rid of the extra, and then go over here to the last one, and oh, it's already got that. Okay, and then let's print this and see if it is what we think it should be. So print I. Okay, so it looks like it works. So now I have that matrix. I can use the linear algebra eigenvalue function. I can do that. So let's do that. I'm going to say A omega W is equal to my eigenvalues and eigenvectors. My eigenvectors are going to be W. It's np.lin. And again, I went over this in the previous video. I'll link that down below. If you want to learn more about doing it by hand, you can do that. And no one wants to do a 3x3 eigenvalue problem. Nobody. Linear alg.eig I. And I don't actually care about the eigenvalues. I really don't. I only want the eigenvectors. Now let's just print out all of them. I'm going to print out W like that just so you can see. And this, in this case, this column is my first eigenvector. That's my second, and that's my third. So let's actually take the transpose of that matrix and print out one of them at a time. So I'm going to say print w.t. It takes the transpose, and then I just want the first line out of that, the first element. So if I do that, that's my first eigenvector. My second one is w.t1, the second element, and the third one is w.t2. And there you go. There's my three eigenvectors. Now let's check it. Let's check it and see if it works. So I'm going to copy these numerical values. I'm going to copy them. I'm going to go back over here to my rotator program. I'm going to go up here, and I'm going to give you this code. Don't worry. Okay. So up here, I set the initial angular velocity vector. I'm going to comment that out, and I'm going to say W equals vector. Boom. Now I have to add these commas in there because it didn't put the commas. Comma, comma. Let's run it. It's running. But you'll notice that these things are rotating in circles, right? So it's rotating and it's behaving. It's not tumbling. So this is what we call a principal moment of inertia, a principal axis of rotation, technically called. It's an eigenvalue to the moment of inertia tensor. And we can see that because it rotates. The angular momentum is in the same direction as the angular velocity, and so it behaves. And that's pretty nice. Okay, let's rotate the other ones. Why not? We should do all of them. So here's the next angular velocity vector. Control C, copy, and I'm going to paste that in right here. I need to put my commas in. And again, there's better ways to do this, but who cares? It doesn't matter about doing it the best way. Okay, it's rotating in a weird way, but you'll see that it is indeed mostly rotating in a circle. Oh, no, it is. It's rotating in a circle. That's pretty cool. See? Okay, now let's do the last one. Just for completeness, I'm going to copy this. And I'm going to go back over here. And I'm going to edit that. And I'm going to paste it in here. Oh, I put a 0 minus. That was weird. That was my mistake. Okay. It worked. And I'm going to run it. Rotating. And that's the direction of the angular velocity. Yep. That's it. Look at that. Behaving. I mean, it's kind of... So, you know, in a lot of situations when we do the eigenvalue problem, you can't really see what those eigenvalues mean, or those eigenvectors mean. But here you can see, right? You can see the rotation. You can see that it rotates correctly. And that's pretty cool. So, now... Yes, it's true that you can't do this in Web VPython because it doesn't have matrix support, it doesn't have eigenvalue support. I mean, you could make your own eigenvalue program in Web VPython, and that would be fun. But you don't have to. So switching back and forth, not ideal, but it's still, I think, kind of fun. So like I said, I'm going to give you a link to the video down below from that previous video where I go over the eigenvalue problem, and I'll give you a link to this 4-mass rotator. You can change these masses and locations to whatever you want. And there's only, I have these sticks, they're not all connected by sticks just because I used a different program and I didn't want to redesign it. But you can change the locations and the masses of all those things, and it will run fine. So you can make up your own 4-body moment of inertia tensor problem and solve it, and it's kind of fun. So there you go. The end. I'll talk to you later.